Hey. All right. Thanks ever so much for dropping by, and thank you, of course, to Andy. And Andy is going to DJ for me since my usual partner, Avelt, has gone walkabout. I'm here to talk to you about our new loudspeaker, the Moya, the M1 Moya, from Vivid Audio. First of all, let me introduce myself and then Vivid Audio. I used to be the senior research engineer for Bowers and Wilkins, and the last piece of work I did for them was a snail-shaped loudspeaker known as the Nautilus. I was very happy with the results that we got from Nautilus, in all respects except the maximum sound pressure level that you could actually achieve with this speaker. My old boss, Robert Truntz, tried using them in a recording studio, and the truth was they just fell apart and burnt out far too easily. When I left Bowers and Wilkins, it was to create professional studio monitors that had the power handling that engineers expect from a studio monitor, but the fidelity and transparency of Nautilus. My first step then, as I had 2 years in the wilderness, as it were, was to design a couple of drivers which would end up being in nearly all the Vivid Audio, well, certainly the Gear range and now the Moya range, the D50 and D26. I'm going to tell you a little bit more about the engineering and principles that go behind all of these drivers in due course. So, in the year 2000, I met up with a South African chap, Philip Guttentag, and he was interested in starting a hi-fi speaker company. Now, by then, it was 3 years since I'd been with BMW, and I was able to rekindle my interest in hi-fi loudspeakers. When I met Philip, he was going to use just off-the-shelf Scandinavian-made drivers, but I said to him, nah, if you're going to do the job properly, we really have to make our own drivers. And it just so happens I've got some designs. Now, if we'd known then what we've known since, would we have ever embarked upon this? Because it is actually quite a tricky business, I don't know. But it has been an interesting journey, and this is definitely the culmination of that journey so far. Right, I'm going to go into the engineering, some more of the engineering details in a bit, but let's just listen to another piece of music.
And this track is Al Di Meola, but playing, it's almost like a jazz rock version of Dueling Banjos with Al Di Meola and Steve Vai playing the two guitars. And it starts off with the old Pink Floyd Wish You Were Here trick of what sounds like a little transistor radio, so don't get too disappointed at first.
to the Nautilus days, I came to the conclusion, after doing quite a lot of tests and listening tests to different code materials, that what was really required in a loudspeaker in order to achieve the transparency that we expected was a freedom from resonance and reflection. Now, in a funny connection with Matthias, who just gave you the little lecture on digital bit rates and clocking, sampling rates, it is, I believe, down to a matter of life and death that we are so well attuned to the qualities of resonance and reflection. Resonance gives you clues about the structure of something that you can't see. You can tap a fruit or a piece of wood and see if it's ripe or rotten. Reflection gives you clues about the distance to something. You make a noise, you hear the reflection, and you calculate instantly how far away it is. Or, of course, the toothed creature advancing from behind, and you hear a little crack, and immediately you know where it is because of the timing difference to your ears. So I think it is a matter of survival. We've evolved to be so sensitive to these qualities. Of course, that means that our loudspeakers have to be free of those effects in order to faithfully recreate the original performance. I like to draw the analogy with a window onto the performance, and it is our job to make that window as clear and colourless as possible. If we look at the loudspeaker, it has this moving diaphragm which actually creates the sound. It moves back and forth, and you get sound on both sides in opposite phase, equal and opposite. But the first element in this, the actual diaphragm, in my opinion, needs to be completely free of resonance. That means, in practice, that its first breakup mode has to be out of band, beyond the highest frequency that's going to be demanded of it or that you can hear. Now, back in '97, when I first started developing these drivers, these high efficiency drivers, I was also looking at the breakup modes, and it happened that at that point finite element analysis and optimization was becoming quite accessible. So we subjected this basic problem of a dome with a peripheral carbon fibre stiffening ring and let the computer chug away and come out with the optimum profile. And I saw this curve and I thought, that's familiar. That looks like a catenary. And a catenary is the shape that you get when you suspend a chain from two fixed points. It's a very natural curve, and you can see it in all sorts of places. It's actually been used architecturally. The Astrodome in Houston, Texas, which sadly was demolished. Prime example, a catenary, thin shell of concrete in a catenary shape with a peripheral high tensile steel cable running around the end. The net result is that the breakup frequency of these drivers is about double what you'd normally expect, 22 kilohertz instead of 11, which is, it's a pretty significant jump. We subjected the mid-range to the same sort of computer optimization, and whereas most people at that point were using a cone with some sort of little dust dome in the middle, what we concluded was that if you actually optimize the whole thing, so the dome and the cone together as a homogeneous material, in this case aluminium, you can push the breakup, again, from 1 and a bit kilohertz up to, at that time, 6, but with a bit of jiggery-pokery now, we can get 10 out of these. All of which conspire to make pistonic drivers which move as a whole and deliver a resonance-free response to your ears. Okay, let's listen to another piece. This is Abel. He's the new Andy.
I'm the new Andy. Pleased to meet you. What do I do in the company?
Abel is our international sales executive, and he makes it all happen. Right. So we've got diaphragms which are behaving in a perfect and pistonic manner, and the sound field that comes out of them as it leaves the diaphragm is perfect as we would want it. But as that sound field expands, or that wavefront expands, in a conventional square box loudspeaker, as the sound expands and it hits the sharp edge, it sees that discontinuity going from half space to full space. It sees that discontinuity in impedance, and a wave gets re-radiated from the sharp edge. And that wave can interfere with the direct sound, and it will cause irregularities in the frequency response. Not only that, but those multiple sources will interfere with the timing of the signal and the imaging that you get from a loudspeaker. Again, as Matthias was explaining earlier, we are as much tuned into the impulse response and the timing of it as to the frequency response. So what's the solution? Very simply, do not have a sharp transition between the front of the speaker and the side of the loudspeaker. If it's a smooth transition, there is no specific point at which you get an impedance jump, and hence no deflection and no wiggles in the frequency response. How big you make that circular baffle doesn't really matter, as long as there's no change, no sharp transition between the front and the side. So if you look at our little S12 over there, it's the same thing, the little green speaker, that smooth transition. And here, again, a smooth material. And that helps give this lovely broad image which you can enjoy in a wide range of listening positions. Okay, another piece of music, please.
So to underline this, we have a piece of music where the placement of the castagnette differs. It's a live recording and they move around.
coming out from the front of the loudspeaker, no diffraction, perfect. Not quite. You have to remember that as much as there is sound coming from the front, there is the same but opposite sound coming from the back. If we allow those two to mix, of course they cancel and you get nothing. If you put a wide enough baffle, of course you can actually end up with a dipole speaker, which you will get some output. But what happens to the sound from the back of the loudspeaker has a significant influence over what comes out of the diaphragm and out into the front field radiation. You have to dispose of that rear radiation without resonance or reflection. So way back in the Nautilus days, I did come up with a solution to this, and that was the use of an exponential tapered tube absorber. And I've got a little demo here to show you how effective this is. If I start talking into this tube, you'll hear the resonances as the sound bounces between the ends. What's happening, especially to this wavefront, is it's coming along and hitting an impedance discontinuity, a little bit like the sharp edges of a cabinet. The solution is this exponential tube. You'll hear the resonances just stop because it behaves as a pretty much perfect resistive termination. If I now, if you imagine now this being placed directly on the back of a driver, it does the job of dissipating that rearward energy without resonances or reflection. We have exponential damper tubes on all the drivers, the tweeter, the upper mid, the mid. The low mid, the exponential tubes actually come up the side here and they go all the way to the top. What about the bass? Well, right back again in the 90s, the challenge was, how do we combine bass reflex with exponential tubes? Bass reflex is a really handy way of getting another half octave of bottom end. And it'd be a shame not to use it. So indeed, when Vivid Audio was started in 2004 with our B1s and K1s, they were reflex loaded enclosures, so they've got a chamber and a port. But the trouble is, and it niggled, you still get this top to bottom resonance as the wave bounces around. So when we started dreaming of a new product, the gear, what would become the gear, I thought, I wonder if there's a way of combining the exponential tube with the reflex in such a way that we get the best of both worlds. Well, it turns out that if you get your taper right, get the cutoff frequency of the exponential tube right, you can actually achieve that result. I'm going to demonstrate it here with this resonator, which mimics a bass reflex cabinet. So that's obviously the volume of air in the cabinet, and this hole here represents the port. If I blow into it, you'll hear the fundamental, the hum, but there are also some overtones. I don't know if you heard those high-pitched notes. And if I blow harder, you can hear those overtones. And those are resonances bouncing backwards and forwards, as opposed to the fundamental resonance, which is the air in the hole resonating with the chamber. If I combine the good old exponential tube with this system, you can hear that the hum is still there, the fundamental is still there. But if I blow harder, you just get a rushing noise with a gradually increasing spectrum, but no hard resonances. So the principle here, you see, does actually work. And it turns out if it's about 4 or 5 times the frequency, the cutoff frequency of the exponential horn is about 4 or 5 times that of the port, you absorb all the chamber resonances and maintain your port output. In Moya, the exponential tapered tube is to the rear, whereas with gear, it was this ostentatious spiral at the top. With Moya, we couldn't possibly have done the same thing. We could have had horizontal spirals, but you know what? We've done that game. We don't need to do it anymore. So what we've done is the enclosure is tapered towards the back, and then it goes back on itself, and then back again. So you do have the exponential damper tube right at the back. And for those of you who've walked behind the back, you'll see there's an indent, a little bit like the bottom of a wine bottle, and that's actually part of the inward extent of the damper tube. Okay, give us something with taut, snappy bass.
Yeah, you asked for it again, and I, of course, don't comply.
Last thought that you think today is already happened. The link between profound and pain covers you like Sherwin Williams. Smokey Joe is broken, drops into your lap, and the big red wasp makes a scan through my eyes like pages. Last night our boy was out there burning up his matches. I saw him in the afternoon sporting a black eye. The universal man with a pistol or a bottle types.
Nice fade. Okay, so we have the perfect diaphragms in a lovely acoustic environment with their rear outputs completely disposed of, and everything should be sweet. They're what I call the first order potential imperfections in a speaker driver, but there are second order. So let's bring in Newton's third law of motion. To every action, there's an equal and opposite reaction. So when the speaker diaphragm moves forward, the same force acts on the magnet and it moves backwards. Now, because the ratio of masses is about 100 to 1, it does mean that the amplitude of the vibration of the motor is minuscule compared to that of the diaphragm. And furthermore, the actual radiative area of the magnet and the chassis is usually pretty tiny. So on their own, they're really not a problem. But the problem comes when you screw an ordinary speaker into a box. Let me demonstrate that effect with a little music box here. So if I wind it up here, you can probably just about hear a little tinkle at the top end. The little high frequencies actually do radiate a little bit. All the fundamentals are lost. But if I won't stick it on a sounding board, it's really clearly audible. And the same thing happens with the loudspeaker. When you screw the chassis, or if it's a tweeter, faceplate, to a cabinet, you get exactly the same effect. And if the cabinet behaved as a perfect, smooth sound source, it might be not so bad. But the fact is that the cabinet is subject to all sorts of structural resonances. And in fact, the coloration from the cabinet would interfere significantly with the direct radiation from the drivers. What's the answer? Well, it's actually really simple. You just need a piece of compliant rubber, a piece of soft rubber, like silicone, to put between the drivers and the cabinet. So all of these drivers have a silicone O-ring between the magnet and the cabinet, and between the magnet and the exponential horn damper. And the effect is just like this. So with the O-ring, without the O-ring. A completely effective way of solving that problem, which actually works very, very well on all these mid and high frequency drivers. The problem comes with the bottom end, the low frequency drivers, because you've got this massive magnet and a chassis that holds, if you've just got a single driver screwed into your cabinet, if you try and put rubber around the edge of the driver, a rubber soft enough to decouple the driver from the cabinet is also not strong enough to hold the speaker, and it will sag like that. What's the answer? Simply to couple a pair of drivers on the opposite sides of the cabinets and link them with a steel rod, or if you can, actually put the magnets in contact. And that way, the reaction forces completely cancel. I can really easily show you the effect. If these are two diaphragms moving in phase, you can see that my body behaves. It reacts completely to that force. You can see it wobbles around all over the place. If I do the same thing in opposition, my body stays completely still. The reaction forces cancel. It's not new. People have been using it in all sorts of engineering applications for donkey's years. Perhaps the most well-known in the present day would be horizontal piston engines, where you've got equal and opposite pistons all moving together. And it does completely cancel out the reaction force. So there are rubber seals around the edge, but they're just to keep the air in, not for vibration decoupling. Okay, another slamming track, please, Ava.
Okay.
Maggie said, dig one more shallow grave before I'm dead. And Maggie said, I'm just looking for a place that I can lay my weary head. There's no perfect end, just time to leave. Oh, Maggie said, they rake the table at the game of love. Maggie said, it's just stupid luck if you rise above everybody sick and dead. Win or lose, my friend, it's so hard to leave. Holding back, what did I get for all of that? What did it count for? Tell me that. Nothing, nothing, oh, nothing, that's a fact. Oh, Maggie said, it's so hard to find the golden fleece to spin my golden thread. And Maggie said, you're preaching to the choir, girl, now you're not sticking out your head. There's no risk in there, darling, please. Holding back, what did I get for all of that? What did it count for?
Please work down to that ear crushing track that you're alluding to all the time.
Okay.
Do your worst.
So, lovely drivers, lovely acoustic environment, nice absorption, decoupled, all that. But they're all individuals.
No, we're not.
They have to be combined into a system. Each one has a range of frequencies over which it gives an optimum performance. And the job of dividing up the frequencies is given to the crossover. Moya, and in fact all vivid audio speakers, are passive. So the crossovers are composed of capacitors, inductors and resistors. There was a time when I believed the only way of doing a crossover properly was active. That was actually, again, the Nautilus days. But pragmatically, when we started Vivid Audio, small unknown company from South Africa, no reputation for high-end audio, my business partner, Philip, whose feet are firmly planted on the ground, said, if we go active, we might as well burn the money. Let's start with passive. And so that's the way it's been. And I've relearned to love passive crossovers because today, with computer-aided network analysis and optimization, it's actually a pleasure to design them. And you can, in fact, do a remarkable job of creating extremely accurate filter responses, especially if you start off with a bunch of good drivers in a nice box. So, until Moya, a four-way was the most complex passive crossover I've done. But as I'll explain later, Moya is a five-way, and now the rules sort of change. It's been an interesting exercise. It actually took me a month to design the crossover for this thing. But I can assure you that through each crossover point, each driver sums perfectly. And the result, I believe, and I hope you agree, is a homogeneity. You can't hear the separate drivers. There is another element to this, is that all the drivers use the same philosophy. They're all made from the same aluminium magnesium alloy, although these have got a bit of a diamond coating on, but they're fundamentally the same sort of technology. And I think that's quite important. I call it the consistency of philosophy. So it's not like having a paper cone bottom end and an electrostatic mid and a bullet tweeter. It's designed as a system. You could stack up a bunch of rails and have a little speaker in front and get, quantitatively the same result. But because Moya M1 is designed as a system, I do believe that it all knits together in a way that is very difficult to do any other way. Right, another bit.
public that we take orders for Christmas delivery?
Absolutely.
Okay.
Your challenge is choosing the right colour. We can do different colours, in theory. Nobody's asked us yet.
Oh, yes, they are.
Different colours?
5 different colors.
Do you know the BMW M series? The 3 different colours. Anyway, right. Comes to the last section. So, the question that people obviously ask is why 8 bass drivers? What's that all about? Does it really have to be so damn big? Bear in mind what I said at the beginning. I did leave BMW to make studio monitors, and as such, these drivers were designed with the efficiency and the power handling to go in a studio monitor. And for me, target should be a loudspeaker capable of reproducing 120 decibels comfortably, which is the sort of level that you can get in a studio. I'm not saying that listen to it continuously like that, but it's nice to be able to get peaks of 120 dB. Well, what does that mean in practice? The drivers are excursion limited. That is to say that so we've got this target of 120 dB. What is the lowest frequency that the driver will be able to reproduce at 120 dB before it runs out of excursion capability? Well, for this D50, it's about 1 millimetre. 120 dB, 1 millimetre, 50 millimetre driver, it's about 1.7 kilohertz. Same rules, this driver, 2 millimetres of travel, 560 hertz. These low mids, 4 millimetres of travel, that means about 130 hertz for 120 decibels, which finally brings us to the bass section. How many C225 bass units does it need to produce 120 decibels at 30 hertz, which is the point of maximum excursion? Bear in mind that it's a reflex, so as you go below 30 hertz, the sound actually comes from the port. The C225 moves about 12.5 millimetres linear excursion, and to reproduce 120 decibels at 30 hertz, you need 8, which is lovely because it just happens to be a tall enough loudspeaker to house all this lot. So there you go. A loud speaker that can also reproduce the finest details. Thank you very much.